of Astro slash cosmology slash gravitation physics together and to discuss what people are working on. So we're going to have 3 seminars today. So Walter, Viviani, and Iago. So I was not here yet. Okay. So we start with Walter Riquelme. Walter is currently a postdoc at IFT UNESP and also CTP-SAIFR. He did his PhD in another IFT, in the wrong IFT.
In the fake.
I like to say the fake IFT. Our IFT is older, doesn't know. So young is the fake. The other, because we are older than them. So the one in Spain, they have an Instituto de Física Teórica in Madrid, in Spain.
Okay.
So and they call themselves IFT, of course. So Walter came from one IFT to another IFT.
Yeah.
Walter is an expert on non-Gaussianities, how to measure non-Gaussianities from galaxy surveys. He's working on the Dark Energy Survey project that he's going to talk about probably, and also in the Legacy Survey of Space and Time, which is a project that is going to start actually this year. The commissioning date should start coming this year, and next year will be the official start.
Hopefully.
I think it's going well, so I think it's going to happen. So Walter, please go ahead.
Okay, so good morning, everyone. So as per you present to me, my name is Walter Riquelme. You can just call me Walter, and I want to introduce you some of the methods that galaxy surveys currently use to extract the properties of the initial conditions of the universe. I will explain a little bit more in detail what that means. But I want to start this presentation with the following figure, where in current times, as you may know, galaxy surveys are really experts now in trying to extract the different location of galaxies across the sky. So here in the figure, you can see, I don't know, it's the original. This is captured by the DECAM, that's from DES. And you can see a collection of different objects that are galaxies. And in current times, like recent galaxy surveys, will extract more and more galaxies. And one difficulty with this is how we can extract information of these maps of galaxies in a more consistent way. And to use this, cosmology has created something that's known as summary statistics, where you can extract information of this and put it in a summarized way instead of looking directly for the maps directly. One way, or one important summary statistic is known as the two-point correlation function, where if this works, the main idea behind it is that you have the map of galaxies in the sky, and then you start to make a histogram of separation of galaxies. So you take 2 points in the sky, and then you start counting how many galaxies are within that separation or within that separation, and you start to reconstruct a function, which is known as the two-point correlation function. And then you start here, you complete the map, you try to compare all the different locations, and then you have a function. And this particular case, for example, you can see actually something that's known the BAO peak. That is something that people use to measure the BAO variable oscillation. So this is a little bit of a summary of the two-point correlation function. And the two-point correlation function has been used in the past for different galaxy surveys to extract different properties of the universe, such as the expansion rate, or the growth structure, or the matter content of the universe, by feeding essentially this two-point correlation function measured from the data and compare it against the theoretical model of this two-point correlation function. In the particular case for galaxy surveys, you have essentially two kinds of galaxy surveys. One of them are known as photometric surveys that are popularized because they estimate the redshift of galaxies by using filters to approximate the spectrum of a galaxy. So, for example, they use take pictures of the sky under certain filters, and then by knowing the amplitude of a galaxy under each of these filters, they can estimate the redshift. And in the other side, we have spectroscopic surveys that estimate the redshift by measuring directly the spectra of the galaxy. So they run a spectrograph to a point in the sky, and then they estimate the spectra, and then without the spectra, they estimate the redshift with high precision.
Excuse me, when you speak
Yes.
about a survey, is it a kind of table that you have, or is it a graph?
No, a galaxy survey is a big telescope.
A big telescope?
Yes, the telescope is known as a galaxy survey because it surveys the sky. So it looks at different positions in the sky and then generates some map. From these galaxy surveys, you can have two kinds, depending on how they estimate the redshift of the galaxies. I will be focusing mostly on this. But as I mentioned before, these surveys have been really successful in extracting growth and different properties of the cosmological universe. But one main question is that what can it tell us about the initial conditions of it? So how can we extract the initial conditions of the universe from these maps? And of course, I'm giving here a big review, so if you want to interrupt me and ask me anything, and then I would prefer to be more in the details in the introduction than to show the result afterwards. So the important part is for you to get the motivation. So about the initial conditions, so what do I mean when I talk about initial conditions? Mostly I'm talking within the framework of something that is known as cosmic inflation. And cosmic inflation is a level of the universe that's characterized by a quasi-exponential expansion driven by the dynamics of some scalar fields. I say some scalar fields because you can have some more intricate scenarios, you can have vector fields or combination of vector fields with scalar fields. But the main idea is that you have a scalar field. Then this scalar field has some evolution across the universe. And over this evolution, you have small fluctuations on this scalar field, and this scalar field, these fluctuations on this scalar field serve as initial conditions for the growth of the structures. How basically you have fluctuations in the scalar field here, and this will be connected to something that is known as a curvature perturbation. And this curvature perturbation serves as backbone of galaxies or other objects in the sky. One main property of these initial conditions is something that is known as the primordial power spectrum, which is essentially in the tuple correlation function of these curvature perturbations. So for example, if you're doing cosmology, like studying cosmology, and then you start to use the cosmology codes, you will notice that you will have to always put some input, something that's known as AES or NS. This is for parameters of the cosmological model. And these parameters is come exactly from these initial conditions. So what you are actually defining, when you define those parameters, something that is known as the primordial power spectrum, the tuple correlation function of these quantumly created fields. So that is what I meant with initial conditions. And what is the main idea? How you go from these initial conditions to actually galaxies. So you have these curvature perturbations. These curvature perturbations under the neutrino limit behave as a gravitational inflation, forming now these dark matter densities, which is you will have a dark matter background. These initial conditions will collapse, and then will make the matter collapse, creating an overdensity of dark matter. And then this dark matter will have some more intricate process, and then create an overdensity of galaxies. So this will turn into a halo, and then the halo will turn into a galaxy.
Why do you call it dark matter at this stage?
Well,
Why do you call it dark matter?
why do I call it?
Yes, what's the reason for calling this dark matter at this stage of the universe?
I mean, this is not, I'm talking more in the old state of the universe. So here, this is not early universe anymore. This part corresponds to early universe. This part corresponds a little bit more later in the universe. But the idea is that these curvature perturbations affect different periods of time depending on the scale that something that's not that it depends on where the scale of re-entering the horizon they change is something like this. But these initial conditions affect different periods of time. So for example, these initial conditions, this is later in the universe when you have, for example, a dark matter background or a matter dominated era, where most of these things that matter, then this becomes into other matter. Other matter density.
Definitely, I mean, you need to have dark matter because if the matter has an interaction with photons, it cannot collapse. So it's crucial that it's dark, that it doesn't interact with photons. Otherwise, photon pressure will prevent the collapse.
But Ricardo, we won't see is right, because there should be delta of matter,
Mhm.
meaning matter plus dark matter. Because that's what you measure, that's what you predict theoretically. The distribution of this fluctuations in matter plus dark matter. And then you have to evolve to galaxies, so G's galaxies. But you're right, I think it should be matter plus dark matter.
Yeah, I think I'm considering here that that matter is so much abundant than irregular matter that an overdensity of matter at this stage, like baryonic matter, will be too small.
Yes.
But yeah, I understand
Thank
the. So then the main idea is that you, in order to connect these dark matter densities to galaxies, you have something that's known as the galaxy bands. So this, some especially sometimes known as a damping variable that encapsulates all the dynamics that create a galaxy in the first place. This is the simplified way to look at it. And yeah, so that's the main role. You have the initial conditions, these become dark matter densities or matter, all matter over densities, and then these become galaxies via the interaction of these galaxy bands, these parameters here. And here's
This parameter can be a function of scale. That's
Yes,
what we're going
yes.
to talk about.
Of course, yes. Given the different interactions in the universe, the behavior of these parameters could change, which will be the main topic of my talk. But I'm going to move over this week. And the main idea then is transferred to the power spectrum. So you have the one power spectrum, then you have the input in your codes. This becomes that matter power spectrum later as the codes evolve. You have your codes, they're going doing their things. And then in order to relate this power spectrum to the galaxy power spectrum, you need to do this galaxy bias again. And here in this figure, you can see the matter power spectrum of a sample of luminous of the galaxies from EVOS and Cosmo. Just as a reference, yes.
More like a prediction, theoretical prediction, or phenomenological prediction?
It's a good question. It could be a little bit of both, depending on how detailed you want to be in your modeling. It has some theoretical motivation, but generally in observational studies, people just leave it as a free parameter, and then it's part of the free parameter that you have in your measurement. So you don't have extra information on it.
No, just a naive question. I mean, that of
Yes.
course, the P of K that you show is from galaxies, no?
Yes.
But I mean, from lensing, no, you can in principle do the same for dark matter?
Create another power spectrum of the.
Lensing matter.
Yes, I would say yes.
And did people have tried? What comes out? It's huge errors? Is it good?
No, I think they do use it. For example, DES uses it for the shear field. They could get the triple correlation function or the power spectrum for this shear, cosmic shear.
Mhm.
And they have it. I don't have a figure around this. They use it for the actual again. They can actually use it to measure cosmological parameters.
No, but I mean, really, the power spectrum on dark matter, can you measure with lensing, or can you measure in principle but not in practice, or you cannot measure at all? I mean,
Yeah, you can measure it but you have to have this here.
okay, and then what is the result? There are huge errors, it's comparable errors. I'm totally naive about this. I don't know.
I'm not 100% sure.
They have density maps,
Mhm.
so it's very low, poor resolution.
Okay,
But the density maps we have from lensing.
okay, but then at very, so yeah, very high K doesn't say anything.
Okay, yes.
It's always more.
So the resolution is very small.
Okay.
Okay. And people actually use these to combine. They combine this cosmic shear with this galaxy or power spectrum, and then this cosmological parameters. This is a 3 times 2 thing.
And that's a bit different from what he's asking, because this thing, what you're saying, is because you measure the shape of the galaxies, and the shape of the
Yeah.
galaxy is sensitive to the amount of dark matter. And then you make correlations between the shapes of the galaxies. But that's a little bit different from what I understood from her question. Her question is that suppose from not shear, but you have a density map, really, from gravitational lensing.
Yes.
And
But this
yes.
map has to be extracted by shear, right?
Yes, it has to be extracted. Yeah, I have to extract the map from shear.
Yes.
That's correct. And but this map,
Mhm.
you could use this map to have a 2-point correlation function.
Right.
It's not shear correlation function, but it's a. it's a correlation
Having
function.
processed the shear.
Yes, it comes from the shear.
Yeah,
But you want to have density correlations, not
Right, right.
shear correlations.
Right.
And I think the resolution is very poor for that.
Also, you have to go to more than scale larger than 10 megaparsec, 20 megaparsec.
Oh, yeah. So, so DS is, you see blobs, right? It's very poor resolution. So, but, yeah. I wonder if people can, I think people can find clusters also. From
Yeah, I
share.
think there are some big have density maps around. Right?
Yeah, definitely maps.
But they never
I don't know if
translate
they compute
into
the storage
PK
space
because it's very small.
As far as I know, I haven't seen that yet.
But I get maybe they will do it eventually. I mean, it's something that can be done. So, okay. Any more questions? So then, as I mentioned to you before, the initial conditions that we will be going to talk about are coming from cosmic inflation. And cosmic inflation serves as a seed using discrete perturbations, and then from discrete perturbations, you will compute the primordial power spectrum. One prediction of cosmic inflation is that for the most standard scenarios of inflation, computing the two-point correlation function of this primordial field is more than enough to capture all the statistics of this primordial field. So you will not only here by computing only this. But if you have like more intricate scenarios of cosmic inflation, you have extra fields, or you have some extra interactions, or different thermal behavior from the primordial fields, then that will induce something that's known as primordial Gaussianism, which implies that we can capture these effects now beyond Gaussian by computing higher order correlation functions. In particular, for this case, the triple correlation function. Where now this triple correlation function its amplitude under some particular approximation that is known the local limit is parameterized by this FNL parameter. So this essentially this FNL parameter will give you the amplitude of this triple correlation function. And this, since it could be connected to different models of inflation autors, some more beyond standard scenarios, this is essentially a window to disentangle between different models of inflation.
Sorry, a question from an outsider. I do not work in the field. This non-Gaussianity or Gaussianity is something that you see in the CMB?
Yes.
Yes.
You could see it also in the same yes.
You test,
You tested
you
it?
test as a CNB.
No, at the moment there is only in upper bound.
Yes, you haven't, there's not been found.
Yes, I'm going to arrive to that at some point, but this is it's something, as I mentioned before, these initial conditions could essentially affect anything that you have in the universe. So the same initial condition, the same power spectrum could enter to the fluctuation of temperature in the CMB, or could enter the galaxies, or could enter different things that you can have in the regular universe. So you can try to see or try to look for the signatures in different stages of the universe. And since all of them are coming from the same initial conditions, they should agree. So I'm a little bit slides more. I will show you the measurements for these coming from CMB. And the main idea is trying to see whether the measurements of this parameter that come from CMB does agree with the coming from the one from Galaxy Service or something. But the main idea is that to measure this, we want to measure this parameter, and this parameter should be help us to see whether maybe we have some models of inflation that goes beyond the standard scenario. That's the main idea.
So the standard scenario has a prediction for FNL, the standard one Kellerfield scenario, which is 10 to - 2 or something.
It depends on the explorer parameters, but yes, it's really small. So 10 to the -2, 10 to the -3. These are really small.
That's why he said that's close to Gaussian. Because FNL is very small.
If you have something more fancy, some scalar with masses and they interact with each other, then you should have maybe a little bit more of a signal. So as I mentioned before, as I just mentioned, you can have these initial conditions, and this initial condition could be transferred to different epochs in the universe of different structures. Could be appearing in the CMB temperature fluctuations, or it could be appearing in galaxies. So we're focusing mostly, or my talk, on how to measure these primordial Gaussianities using something that is known as a large-scale structure of the universe, which is entirely a fancy word for the galaxies or different other traces of matter at large scales. And the main idea is that, as I mentioned before, the triple correlation function is essentially a way to capture these primordial Gaussianity. So you might be wondering, okay, maybe we can try to start counting triangles in the sky, trying to see the looks of the shapes of these triangles, and trying to capture maybe primordial Gaussianity from this method. The tricky part is this is maybe not the best idea because as the universe evolves, this leaves an imprint of non-Gaussianity already that's come from the gravitational evolution. So gravity will produce that these galaxies that were created under Gaussian initial conditions, they will start to evolve, interact with each other, and then you will have another source of non-Gaussianity due to this interaction. So the tricky part is how to disentangle the non-Gaussianity coming from the evolution of the universe with the primordial Gaussianity coming from the initial conditions. This is really difficult in general because you have to do a lot of modeling of the structures and the dynamics of the structures. So the remaining question is what can be used to measure then this FNL parameter on the useful galaxy. And with this, I'm going to this main function that we will be using, which is known as the scale dependent galaxy mass. And again, as I mentioned before, you have the initial conditions, they become the matter over densities, and then these are matter over densities in order to connect them to galaxies, to introduce something that is known the galaxy phase, which in principle could be measured directly or which have some theoretical motivation. The interesting part is when you have primordial Gaussianity, this effect of primordial Gaussianity parameterized on this function, which is the local limit of primordial Gaussianity, essentially induce a coupling between long wavelength modes and short wavelength modes, where the long wavelength modes essentially are related to, or usually are related to the galaxy bands. This is a really schematic behavior, but the main idea is that it comes from also, if you are experts of these, come from the pressure checking mechanism. So you have a lot of the evolution of how these over densities become halos. This has a particular function. But now, if you have primordial Gaussianities, this FNL parameter will couple long wavelength modes with short wavelength modes, introducing a variation now in these galaxy bites. Then, as a summary, then the introduction of this primordial Gaussianity will change the relation between the matter and galaxies, where now this P will not be a constant anymore, and now it will be a function of both FNL, and it has this particular behavior of K Q squared.
So in your diagram, these fluctuations are the non-Gaussianities or no?
In my diagram, these are the fluctuations of the over densities. So the main idea of this figure is to schematize how the matter over densities become into halos. So these are, for example, this could be some position cues, essentially like a time coordinate. And here you have, for example, the random fluctuations of density field. And the idea of how this density field becomes a halo or a galaxy is that these fluctuations have to surpass certain threshold. So this will be basically randomly moving around because they have like a Gaussian initial conditions. It will be basically noise. But then this FNL parameter will induce some large scale behavior, some this background wave that will essentially push some of the fluctuations to pass towards this threshold. And so that's a little bit of the schematic summary of how these long wavelength modes affect these galaxy bands. So essentially, this long wavelength modulation is coming from this FNL parameter, and this will introduce this scale-dependent bias to the galaxy bias that it has before. That's the main idea. It's a little bit more convoluted in the practice, but this is the main function that we will be trying to do.
So what is M of CFR?
Yes, M of Z is a function that basically encompasses all the things that depends on registry. And here we have some effects of the growth factor entering. I think it has some constants around. So this is just one schematic that it has to mention that this also depends on registry.
So if the galaxy bias is 1, there's no effect. Is that
Yes. But a galaxy bias. I mean, the structure with galaxy bias 1
yeah,
are not galaxies, right?
yes.
To have galaxies, you have to have more than one.
Yes,
Traces that have bias equals to 1 are not.
yes, but there is an effect, okay, I understand that, but is there a reason why FNL doesn't appear if A equals 1? Well, this P parameter can be anything, right?
Yes. So in here, there are a lot of details about this formula, basically about the functional shape or the behavior that it have this P, which have improved, that it depends basically on the traces that you're trying to look in your survey. For example, for luminous galaxies, this P is 1, for quasars, this P is 1.6. It changes a little bit in the modeling, it's still in the open discussion of whether this is possible or not. It depends on the traces.
Okay.
But that was your question of what
Yeah.
on that direction?
Yeah, I have another question, because this
You can just ask.
this
You can
long,
just ask.
long-
How
yeah,
much light will there
this long wavelength perturbations, right? They also exist in the Gaussian universe, because we have a super sample, what's called super sample covariance. Modes that perturbations with modes that are larger than the horizon. But these appear also when it's Gaussian. So is there any particular distinction between Gaussian and non-Gaussian?
Yes, the main difference is not that, of course, you will have in both, in the universe, you will have long wavelength modes and short wavelength modes
Yes,
by itself.
regardless, yes.
The tricky thing is this FNL parameters couples both of them.
Ah, okay.
So the
Okay,
effect
so
of
how-
this is the coupling between them.
Okay. Okay.
That's what produces this particular effect. So then what is the effect of this galaxy bias and what is the effect that we want to try to capture? Essentially this, as I mentioned before, you have the power spectrum, and this is with different values of FNL coming from these scale elements. So you can see here in blue is the regular power spectrum that I showed you before that come from the galaxies with FNL equals 0. So there's no signal of these parameters. But then in orange, you have this FNL of 1/2. So you can see that you have this rising at large scales in the power spectrum, where this is the effect that we want to try to capture. And as I mentioned before, we focusing mostly in the two correlation function, and the two correlation function is the Fourier counterpart of the power spectrum. So you can you can do one and the other. You can stand one and do the other. And you can see also that we have a similar behavior for the triple correlation function, where now we have this rising at large scales in blue again, no remote vicinity. But then in orange, you have this effect of FNL 100.
So what is this negative dip when FNL goes minus 100?
That's a tricky thing. So as I mentioned before, this effect goes with FNL,
Yes.
but the galaxy bias to the power spectrum enters with P squared.
Yes, yes.
So for example, you will have one term that is FNL squared, and then you will have a term with FNL only FNL.
Okay.
So the FNL squared at large scales will become basically 100 and not minus 100. You will not see the minus sign on it.
Right.
And then it will overcome the minus.
Right.
So then you have this dip here.
Okay.
There is something that I will also here around. This is starting to rise up at the large scales.
It can go to 0, basically. Roughly.
Yes, yes. So it will. I think it will go to 0 to 1 and then we'll just.
Yeah, since it's the square, it goes to 0, just bounce.
Yeah, I think it's. So this is something that has been used in the past to capture these FNL parameters. Here is the main summary of people measuring these FNL parameters. In orange, you have the measurements, as I mentioned before, that I said that I wanted to mention. This is the measurements coming from CMB experiments. This is, you have the CMB map, you compute the triple correlation functions, and then you start to lower the errors in this FNL parameter, which until you get here to the latest result from here. And in blue, is the result of this FNL parameter coming from large-scale structure surveys. That is using this scale-dependent bias method to measure this FNL parameter. And here you can see essentially the difference between the latest results and the black results. One tricky thing is that CMB experiment already reached the cosmic variance limits, implying basically that the constraints coming from the FNL parameter will not improve anymore. And the errors in here, I think it's around 5. Is centered in 0 around 5. And another interesting thing is that all these constraints, SDSS, both EGOS and EGOS, are coming from the spectroscopic surveys. But as I mentioned in the introduction, we have two kinds of surveys, photometrics and spectroscopics. So photometric surveys, there are some words that say that photometric survey could be playing a big role in breaking this sigma FNL equals 1 barrier, mostly because of the number of objects that they can capture. Why is important this barrier? Basically, as I mentioned before, because if FNL is close to 0, this implies single field inflation, but in less scenario. But now, if you have a detection of FNL, for example, of order 1, this will imply immediately that the cosmic inflation is beyond single field. It's not single field. There are some theorems about it. And so if you have a detection of FNL, this implies that we have a beyond standard scenario. What we don't know, but at least we know that it's not single field. That's the biggest smoking ground that we are trying to look for in this kind of framework of people working in these things. So as I mentioned before, photometric surveys could play a big role, and I'm going to present to you the results or the starting result of forecast coming from the dark energy survey, which is a photometric survey located in Cerro Torado, Chile, that covers an area of around 5,000 degrees, and it does photometry in 4 color bands. So as I mentioned before, a photometric survey just basically is a big camera that takes pictures in the sky under different filters. And by comparing the amplitude of these filters of each galaxy, they can estimate the redshift. So here, for example, you can see in black the spectrum of an elliptical galaxy at redshift 0.4. And in orange, or in the different colors, you can see how TS estimates the redshift of this elliptical galaxy. These are the 4 filters that TS has. And here, by marked by star, you can see the amplitude of these points. So the idea then by DES is that by using these points instead of the full spectrum, they can estimate that this is a galaxy coming from redshift frequency.
Sorry, once again, an outsider.
Yes.
Question, right? About the survey that you told me it's the observatory.
Mhm.
But at the end of the day, you go and ask him for some data, right?
Yes.
You ask the survey for some data, and that data is written down in tables on.
Yes.
Yes.
Yes. The big data that we have is a collection of tables of the location of each galaxy, of the whole map of galaxies.
Like 300 million galaxies.
So these points, some of the points.
We call properties, no, each galaxy has several properties, so
Computational.
it's completely computational, you cannot do this.
This is basically data
Can,
science.
can you look at 300 million points by eye? Not even string theorists can do
It
that.
depends on the distance.
Resolution.
Yes.
So besides the location of the galaxies, we also have the amplitude of each galaxy under each of these galaxies. So you have the stars, basically, for each galaxy, for each object that we see. And the interesting thing is that combination on the amplitude of these, each galaxies, can be used to estimate the redshift of the galaxy, the location weights in the depth of how far it's from us. And of course, in here you can see how the footprint has changed under these. They have been taking data for 6 years, and then right now we are preparing for the latest, the final result of the final basis. One interesting thing that the dark energy survey has is that by using this color selection that I mentioned before, that each galaxy has, we can define different galaxies. So we can optimize the color selection of the objects that we're seeing, depending on the signs that we want to extract. For example, there is a sample that is called the BAO sample, which is optimized to measure, to extract the galaxies that improve the results on the variables considerations. And then we have another sample that's known as a McLean sample, which is optimized for something that's known as a galaxy-galaxy, which is a combination of galaxy clustering and cosmic shear. The combination of both. One interesting thing is that then, since the photometric surveys have uncertainty on this redshift due to this, since it's not a spectroscopic, you have errors in the estimation of redshift. And galaxies tend to have something that's known as a tomographic redshift. So each galaxy sample is separated in beams. So instead of knowing the exact location of a galaxy in redshift, we just know that for example, certain galaxy belongs to this redshift beam, and this galaxy belongs to this distribution. We don't know the exact location, but we have some shells that are made to essentially capture this kind of behavior. So the big question is, can we use the kinetic survey to measure this FNL parameter that I've been bothering you about a lot? And I'm speaking on behalf of this essentially working group within the ES, and I will be talking about the angular correlation function and mostly on the sample optimization part. So this will be published before. We have this, this work is the one that I've been talking about to you today, and it has essentially three parts. One of them is the definition of the angular correlation function. Then we will have something that's known as the integral constraint, and we will study the impact of the integral constraint. And then we perform some robustness methods to see whether our modeling of this probability was accurate or not. So first of all, what is the angular correlation function? At the introduction, I'll bother you to the two-point correlation function, which was basically pair counting of galaxies. This is essentially the same. Is a galaxy, is a summary statistic of the clustering of galaxies, which is defined by this function. And the main characteristic is that this angular correlation function is a two-dimensional projection of the already mentioned two-point correlation function. So the two-point correlation function was three-dimensional. You were having the whole catalog of galaxies and counting pairs. This instead is a two-dimensional projection of these. So these are made using 2D maps. And the interesting part is this angular correlation function is also affected by this remote opacity parameter, this FNL. In blue, you can see the curves of FNL equals 0 for the angular correlation function, and then in orange you have 100, and then in green you have minus 100. So this is something that we can actually capture from the ES. In order to test our methods, we will have two sets of simulations. One of them are known as the Escola boxes, which are simulations that basically the main properties that they resemble the properties of the ES, implying that they have the coverage, the angular coverage of the survey, they have the same redshift errors, and so on and so forth. We cover the same area. And the other set of simulations will be simulations that cover a little bit of a smaller area. But the particularity of the simulation is that this will have FNL imprinted in them. So we will use the simulations from Escola, the realistic ones, to see what are the errors on this FNL parameter. And we will use these simulations to see whether our method works or not, and whether we will recover this FNL or not. These will be the two simulations that we will be using. And again, you have galaxy pair counts, you have the simulations, you start to count in each of the location of the galaxies in order to construct this two-point correlation function. You do an histogram, blah, 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 you compute it, and then you will have the angular correlation function. So this was as an introduction, but this is something that is known as the estimator of the angular correlation function. It has a particular shape, and the main idea behind it is that you start to count pairs of galaxies. So the main idea behind it is that you have two sets of simulations. You will have the data simulation, you have your simulations that I already mentioned, these are square simulations or the Goliath simulation. And then you will also have a randomly distributed simulation, which is essentially covering the same area, but it's just random distributions. And the idea of this, how we estimate the angular correlation function from data, is by using this. We will count pairs of galaxies coming from the data and kind of weight them with the pairs coming from this random simulation. The idea behind this estimator is that it's defined to describe the angular correlation function as an excess probability of a randomly distributed sample. So something in practice is correlated if it is some extra correlation beyond the randomly distributed sample. So this is something that is trying to capture this. This is the estimator that's trying to capture this.
Just a curiosity, when
Yes.
you said that you used the simulations that were done before, You have to run all the code again, or you use just the output of the simulation?
No, I already have the simulations. We run the simulation once. We have like 2,000 length for one case and 200 for the other case. And then we will not change anything. The thing that we change is the measurement of the galaxies. So each simulation, we have a different estimator of this.
Yeah, but the simulation were done before and they leave the code available and you run them, no?
It's a little bit of a team, right? There's people that it works the simulation, they code the simulations and they create the simulations for you. And then they will give you the simulation.
Okay.
So the main idea then to measure this problem authentic within the S has this basically these three parts that I'm going to summarize in the last 10 minutes I have. The first part will be about the integral constraint. The second part will be some validation using these simulations. And then I will finish with the galaxy sample optimization. So let me start with the main problem that we encounter when we're trying to measure the FNL for the dark energy survey. And this problem is known as the integral constraint. The integral constraint is basically a property that the two correlation function has for the galaxy surveys that they measure when they are measured over a fixed region of the sky. That's the main problem. And the problem is that when we try to measure this angular correlation function from data, it should be integrated to zero. The two correlation, yes. This is the main property that data has, which is basically saying that the power spectrum coming from these galaxies at really, really large scales, at some point you will not have more galaxies because you will reach the window and then this power spectrum will go to zero. This is something that you can see basically in the galaxies in the theoretical modeling for the Gaussian case, where at large scales the power spectrum for galaxies go with this scale to NS, where NS is close to 1 at large scales. And you can see basically in theory that this goes to zero. But the tricky part is when you have this Gaussian thing. So as I mentioned before, this scale-dependent bias introduces this one over k square behavior. And basically for this case, a particular power spectrum will go, when we go to k to zero, we see that you will have some kind of divergence here at large scales. That will be proportional to the ZNL. So this is a complicated effect that the theory has, but the observational side doesn't have. So this implies that this integral constraint needs to be imposed to our theory in order for both the observational and the theory to be in the same footing. So this is mentioned before. Instead now the integral constraint condition essentially is this integral of the angular correlation function over the hole's footprint mask. So this fact, as I mentioned before, the ES has some shape of the tank. So over the integration of this triple correlation over this map has to go to zero. And this is basically the condition that we need to impose. In here, you have this R here, which is basically known as the random pair correlations. It's the thing that I mentioned before, this pair counting or coming from a randomly distributed simulation. But the main idea of this is that these random pairs basically inform you about the shape of the survey. So instead of doing a really complicated integral over the footprint, you basically use this combination or conclusion between the random pairs and this angular correlation function as a way of integration. So then you have integration here of the random of the whole survey. This is a simplified way of using the of computing the iteration. And then we need to move this integral constraint to our theoretical modeling, implying that we have to introduce this constant and or this parameter, and this parameter will be defined this way. And what is the effect of this? We should be doing this. So now, in order to test the importance of this parameter, we will be testing on the Goliath simulations. And you can see it basically here. In blue, you have the angular correlation function measured from 100 simulations. These were the simulations that have FNL 100 as initial condition. And in blue, you have FNL, for example, for this case, FNL equals 100. In orange, or in green first, you have the theoretical modeling that I've been bothering you about, with this FNL, but without the integral constraint condition. And then in orange, you see what is the effect of introducing this integral constraint into your theoretical model. And you can see at least by eye that the orange curve agrees much more with the blue curve. This is basically because of the integral constraint. This is a similar case, but for FNL minus 100. So then up to this point, this suggests that the integral constraint could be really important when we try to measure this FNL parameter. Just a little summary slide of how we will measure this parameter. The measurement is based on an MCMC sample of a Gaussian magnitude, where the Gaussian magnitude will be essentially depending on this, both on the FNL and the different galaxy bias parameters. This is just to give you a little bit of the flavor that the parameters that we will be measuring. Mostly because we have FNL here in this definition of the galaxy bias, and we also have the linear galaxy bias, which is something that we don't know a priori. So we will feed it as a free parameter. Someone asked before, so you have this galaxy as free parameter and both FNL.
But
So what-
you're allowing the bias to change from mean to mean, right?
Yes.
But FNL, no, of course.
No, FNL is supposed to be like one or something. Yes. So now in here, the thing that you saw you can see it here now in the constraints or the measurements or the significance. And here you have the contour plots for both the galaxy bias and the FNL parameter for the particular case of the Goliath FNL 100 simulation. First of all, in green, you can see that if we don't include the integral constraint in our parameter, we get an FNL value of around 0 for the simulation that was supposed to have FNL 100. But now, if we include the integral constraint in this purple curve, you can see that we essentially recover FNL 100 that it came from the simulation.
So just a question, so data vector you're using is one simulation or the average of the simulation?
The data vector for this particular case, it was the average of the whole. So that's why the contours are small.
Yes.
Yes. So the main conclusion from this then is that the integral constraint is actually essential to avoid the bias of this FNL parameter.
Is there a way to understand why without putting the constraint goes to 0?
In both cases?
Yeah, both cases.
Yeah, I'm not really sure. Maybe, let me see it. Try to see it here. I think one way to see it is that this integral constraint damps a little bit the effect of the FNL, then this will imply that order doesn't bear. Yeah, I'm not sure. Not sure.
Just curious because.
Yeah. It's more like some mathematical effect.
Yeah, I think that is curious how.
Yeah, I'm not 100% sure of why this is happening.
But the way to do it is in the other plot, previous plot is to show what the angular correlation function is for FNL equals 0, right?
Right.
You don't have that, but it should be very close. We had one in a previous plot.
Yes.
So it should be close to what you get without the integral constraints. That's my guess.
Yes, I will guess so, because the integral constraint, since it depends on this FNL parameter, is almost 0 for when you don't have it. So this is the tricky thing. But yeah, I agree that it should have some functional behavior, but I'm not really sure why it looks like that. That's a good question. I will think about it.
Louis has a question.
Are you around?
He's around.
Hey, what everyone?
Hey.
I didn't really understand what is integral constraint actually. It's because you have because for the P of K, like the very large scale modes, they are not observable, right? It's not something that you observe. It's something that depends on the gauge that you choose. Like there is something like this, right? So why does it show up as something observable when you go in the 2-point power spectrum? Yeah, I don't know if I'm very clear.
I got lost a little bit. So you were
Because
wondering, can you say it again?
because for the matter power spectrum, the P of K, the very
Yes.
large scales, like
Yes.
the like when K goes to 0, is not something that you can observe. And I
Yes.
think it's actually something that is gauge dependent. If you are in the forgot the name, like Newton gauge or some other gauge, then
Yeah.
you get different values, but you don't care because it's not observable.
Yes.
So then how does these very large scales become something observable in the correlation function?
Um, I mean, the tricky thing here is that these integral constraints appear as a condition that they come from the data, right? So when you say that the power spectrum will go to 0, it's a theoretical effect, but the data, no, sorry. The power spectrum going to 0 will go because of the data. So you will have at some point, you will have no modes at large scales. And similarly, for the Turing correlation function, you will also have no more galaxies beyond the separation, for example, of the footprint. So this observational effect is the integral constraint, but this is something that your theory will not have a priori, right? So for example, for the case of power spectrum, people use these window convolutions. And when they introduce this window convolution, this is a fancy way of saying that they're introducing the integral constraint. I don't know if I answered your question, but I think I can understand that much of the confusion could be coming from this part.
Okay, yeah, maybe. Okay, I think I understood a bit. It's more related to the size of the survey,
Yes.
not really K to 0. It's something that is, yeah, limited by the size of the survey. Okay,
Mhm.
thank you.
No, but K going to 0, I understand it's not observable, no, the limit K,
Yeah.
strictly speaking. But you know, from linearized perturbation, we do expect that, no? You expect that a very small K linear perturbation would be applicable.
Yes.
And in linearized perturbation, P, okay, goes to 0.
Yes. That's exactly the point, right?
Okay.
Yes, I think okay.
The thing is that in theory, yes, in your data, no.
Well, in the data, you cannot really know for sure.
You cannot know for sure, but we're interested in larger scales because of the 1/k square enhancement. So it has to make sure that this integral constraint is obeyed in the data as well.
Yes, but the tricky thing is that I think in the power spectrum, both of them will go to 0, but they might be go to 0 at different scales. So for example, the power spectrum will go to 0 when the server footprint, you don't have more data, right? You cannot put more modes. And in theory case, it will be, you will have a disagreement between, because the scale that will go to 0 will be depending on your volume, right? I think that's the tricky thing about this effect.
But at the same time, if you see effect on non-Gaussianity that ultra scale, that should sound fishy. No, come on. You don't expect the non-Gaussianity to be stronger, but ultra large.
Yeah, yes.
I mean,
But physically, it means that you don't have correlations when things are really far apart. Is that
Yes,
that's the physical?
but then you will have the other side that in the survey, they will go to 0 not because you don't have a more allowed most. You will go to 0 because you don't have the survey is small and you don't have nothing else there.
Yes.
But this implies that it will be like a complete survey. You will have these modes
Right.
in theory,
Right.
but in the data, no.
Yes.
I think that's the tricky difference. But yeah, thanks, Wayne. I will start a little bit your question. Now you can also write me.
no, it has to be true that we don't understand gravity in the ultra infrared limit, right? Because of the cosmological constant. So expectation might fail badly here.
But there's this issue that Louis raised about people don't think usually about this, but P of K is not observable. It's gauging, yeah, it's not gauging.
Mhm.
We don't care about this usually. Because we're
Oh, I see.
inside the horizon. Who is right? If you're close to the horizon, then it's gauge dependent. Everybody that went to Geneva knows that, right? That's the roof tourist thing.
I see, I understand. Thanks.
So we have to be careful, there's people from.
No, I have to study about it, yes, so we'll ask you later to get some reference about it. Think about this problem in these kind of situations. But yeah, as I mentioned before, data reconstruction was really important, so now we can.
Yeah.
Uh,
Yeah, I think.
We will just move to the side of the realistic
Nice
scenario.
legs.
We'll move to the realistic scenario of the Explorer simulation. So again, this was simulation that resemble the properties of the dark energy survey. And here you can see how the angular correlation function looks for these set of simulations that are realistic and they look like the dark energy survey. So in blue, again, the angular correlation function without any interval constraint correction, with an zero simulation function, which should have, because the simulations are made over Gaussian simulations. And in green, you have again the theoretical modeling without FNF0, with FNF0 without interval constraint, and then in orange again, we have the simulation with FNF0 with the interval constraint. And the interesting thing that I can show you here is that even for simulations with FNF0, you still have some effect of the interval constraint, even though in this case it's a lot smaller than the previous one from here, for example, like the difference is not that large, but you still have some differences at large scale. So the important thing here is that these interval constraints is even important for when you're trying to go to large scales, even when you don't have a one number sensitivity. But here we are talking about really large scales. So usual measurements of the within the ES, just as usual measurements from the variable oscillation peak go only to 5 degrees or 7 degrees. This is something that DES usually measure. More than that, they don't do. So we tested our method against the importance of the data constraint. We tested whether we can use some more fancy modeling in this scale, or we also tested these scale choices. So from where to where basically we measure this FNF. And here is the results, as I mentioned before. The interval constraint is also important for this for the case of FNF0 simulations when you have this shift on around 7. And we also tested some modeling behavior. One interesting thing is that we show that, as I mentioned before, usual measurements of the ES go to 5 degrees. But if we try to go to the angular correlation function and we compare it to 20 degrees, we have an 11% improvement on the errors in this number, just by going to large scales. So with all these methods and tested and results and blah, blah, we were able to show that we can forecast an error of FNL of 31, which is much difference of the 5 that we were looking for, but when using the Y3 VAO sample. So one interesting remaining question is that what about if we use other galaxies instead of the VAO sample? That was just only one sample. And this will be the last part of my talk, where the main idea is to look for a galaxy sample that using the latest data of the ES that lower these errors in the FNF. So as I mentioned before, one property of dark energy survey is that you will have a selection of galaxies and you can put, you can essentially select different samples depending on the amplitude of the galaxies on the different color. And we will use this particular color selection that is known as the Maglev selection, which is to select basically all the galaxies that has an amplitude on the I band. This is one some kind of it's one of the redshift filters that we use to measure these galaxies. So we will select all the galaxies within this threshold. So we can change, for example, A and B, and this will define different galaxy samples, basically. And this will be essentially a function of the redshift. This particular color selection is really useful when you try to capture galaxies that are like a really high redshift, where you have high uncertainty. So it's usual that if you use some other selection, you will have your number density of galaxies at high redshift will be really low. This particular color selection will allow you to capture more galaxies in the high redshift side. And the idea then of this optimization is to change both A and B and to see whether and see how the constraints or how the errors in this parameters changes. For example, the idea will be something like this. We have here the sample, then we have another sample, and then maybe we have an optimal sample. And this is the last part that I have. In here, you can see how the errors in the CFR parameter changes from the Y3 sample, which was the first part, to the magnitude sample. And then in here, you can see how it changes for different values of both A and B, the ones that I showed you before. And interestingly enough, you see that you have an improvement on this error FNL that it was 30 something before, now it's around 14. So we found 56% improvement just by changing the galaxy sample properties or the galaxy sample selection. And then you can see here that from this we can select an optimal sample practice. What is one interesting thing that you might be wondering is that what's the big jump in the errors in FNL? Mostly because, of course, one of them is that this was Y3 DS, was only up to the third year of data. These are based on the Y6 DS, so you have more galaxies and more objects. But the main difference is this, the comment that I told you before, that this magnetic sample extended, which is this variation of the parameters, has a higher value and higher redshifts, allowing you to capture more effects or more galaxies at higher redshifts. And since going to higher redshifts is essentially a way of proving larger scales, you have more modes at larger scales where it's essentially where this FLM parameter lives. So this is one of the points why the error is lower that much. And with this, we were able to define this sigma FLM of around 14 or forecast this FLM of 14 for the next years of the galaxy survey. So I wanted to leave you here with the conclusions. We talk about three main results of this angular correlation function beside the introduction. We have the importance of the interconstraint. I also summarize a little bit some validation method that we use besides Scholar simulations. And then in the last part, I just show you some results coming from the galaxy sample optimization. So I want to leave you.
Question for the author.
So, just to confirm, this integral constraint.
Yes.
Divided by the theoretical angular correlation function with those random
Yes.
angular correlations. But those are obtained from your simulations, right?
Yes, basically yes. Also, I mean, these are not essentially a simulation. So the way to obtain it is that you will have the survey footprint for certain galaxy survey, something like this, for example. And then you will have, this is known as a mask of the survey. And then what they will do is probably this with random points, randomly distributed points. Just a lot of them. And then I will obtain this random person from this. This is not essentially a simulation because it's just random points over a footprint. But yes, I will do this from the.
About the analysis,
Yes.
how do you obtain that inverse covariance matrix?
I compute the covariance matrix with something that is known as Cosmo. It's a cosmological code that essentially a little bit of a black box for me. I just put
It's an analytical covariance matrix based on a Halo model.
And then to inverse it, to do the inverse of this, I use a Python notebook, a Python code to this linear algebra package. Louis has a question.
Louis.
Yes.
Hey, thank you, Walter, for the great talk. So you said you have the forecast, but did you already try with the data to get the measure?
It is a good question. So for the DSY6, we are not trying it with data yet, because mostly we need to deal with something that I know that's observational systematics. So it's all these observational errors could be transferred to the measurement. So we need to clean for that. And In order to do that, this is something that I don't do myself. This is something that does other people for DES. And the tricky thing is that all the people is busy doing the main result from the dark energy survey for the latest data set. So I'm kind of waiting for them to continue with this and do the measurement with the real data.
But the systematic maps should be available for your six. no?
Yes, they're available, but the tricky part is to compute their weights. So the latest version of the weight is already now recently around.
The weights.
Yes. But people is still busy with the other.
Because
So
with the weights, you can do everything.
yes,
All you need are the weights.
yes, I guess so. But
And it's coming end of the year, so maybe this is a good
we
project.
will push her to do
This is a
the.
good project to finish at the end of the year.
And you also have, I guess, a big degeneracy with the galaxy bias, no?
Yes, of course.
So how do you deal with that?
How are we planning to deal with the genesis of the galaxy bias? The quick answer is that we don't do much about it. So officially, in all the constraints that I showed you before coming from other photometric surveys, they just leave the galaxy bias as a free parameter. So the errors on FNL are with including the genesis with the galaxy bias.
You marginalize compared to the galaxy. Sorry.
Yes, but still, yes, we marginalize over the galaxy bias, but the galaxy bias is a free parameter here. There are, of course, other ways to measure to improve the measurements of this parameter by using multi-tracing techniques or combinations that will help you to better constrain the galaxy bias. So it's something that we're actually planning to do at some point. But right now, for the particular case of DES, we have nothing like a really set plan of how to deal with these degeneracies.
And is there a plan also to use the bispectrum? Because
So far, no.
Not us.
Not us at least, because mostly the bispectrum for photometric surface is something that is really difficult to compute. And as I mentioned before, it's really difficult to model because you will need to introduce nonlinear modeling in the scales and different kind of effects. So for the particular case of DES, we're not planning to do anything with the bispectrum.
okay.
I'm thinking about it. We discuss this like from time to time, but this is it's still a difficult.
Yes.
It's not as validated as this kind of method that have been used before for other galaxy surveys.
So in LSST, there is a group that
Yes.
is dedicated to bispectrum.
Yes.
From Mexico.
Yeah. But they're not planning to look for FNL yet, I think. So at least we have this I mean, there is room to play with here, but the main problem is the theoretical modeling of the bispectrum, as I mentioned before. Because it involves a lot of convoluted integrals, nonlinear modeling, nonlinear galaxy bias.
And the measurements of these triangles.
Yeah, the measurement is also difficult to do. So it's a method that's not that well validated as that power spectrum or as a tuple correlation.
I see. Thank you.
Thank you. Nice to hear from you.
Any more questions for Walter? Okay, so thank you, Walter. Let's break for the next one. So let's say 11:25. Are you sharing that one?
You are the next speaker, right? So you can already set up. Yeah, maybe.
Just try to relax, working back. Mine is just to zero constraints.
Yes.
Things into sanity.
I